Welcome to Greenleaf Entertainment. Time travel has traditionally been the domain of science fiction, not physics. Fortunately, however, at least within Einstein's theories of relativity, discussions of time travel are open to physicists as well. Special relativity unifies the concepts of time and space. General relativity goes beyond unification and allows time and space to warp together in the presence of matter. General relativity even permits sufficient warping to allow closed time-like curves. These seemingly perverse trajectories describe paths through space-time that always move forward in local time, that is, an observer's watch always runs forward, but eventually end up back where and when they started. A space-time that contains closed time-like curves, localized in one region, can be said to have a time machine. Closed time-like curves appear in explicit analytical solutions to the Einstein equation of general relativity. Previously, such solutions were deemed unphysical, simply because they contain closed time-like curves. Nevertheless, since these solutions obey the field equations, they should not be rejected out of hand. Indeed, interest in closed time-like curves has increased in the past decade. The reasons for this are varied, ranging from the practical, if time machines can be built, they would have a lot of potential uses, to the theoretical, perhaps quantum gravity can say something about the existence of closed time-like curves, or vice versa, to the philosophical, do the laws of physics allow or prohibit closed time-like curves? Traveling forward in time is easy and does not require much new physics. In Newtonian physics, with its absolute background time, we all travel forward in time at the rate of 1 second per second. Special relativity allows us to travel forward in time at faster rates. The so-called twin paradox is an excellent example. While one twin remains at home in an inertial frame, the other zooms off into the universe, and then back home, at relativistic speeds with time dilated by a factor of 1/1 v2 each way, where v is the traveling twin's speed and c is the speed of light. On returning home, the traveling twin, having experienced much less passage of time than the stationary twin, has gone into the future relative to the first twin and all other occupants of Earth. This form of forward time travel happens quite naturally all the time. High-energy particle showers formed in the upper atmosphere by cosmic rays contain particles whose lifetimes are much shorter than the time it takes them to reach ground level, but whose speeds are extremely close to the speed of light. The very fact that we observe these particles at ground level means that their rate of time passage has dilated, or, equivalently, that they have traveled into their future. Although going into the future is straightforward, we also need to go into the past, which is difficult, to make a closed time-like curve. This is where general relativity, or, more precisely, the possibility of non-trivial spacetimes is required. Conversely, if closed time-like curves exist, then a traveler can go back into the past. Note that there is a distinction between going back into the past, discussed here, and going backwards in time, that is, having one's watch tick backwards, which is a separate issue with its own physics. There is currently no evidence that closed time-like curves exist. For instance, we do not see future tourists coming back to visit the present. However, it is not in the tradition of physics to turn the argument around and use this lack of evidence to argue that they cannot exist. What about the paradoxes of time travel? Can they be used as evidence against the existence of closed time-like curves? The most serious of these is the grandparent paradox. In this scenario, a time traveler goes back in time and kills his or her grandparent before he or she has any children. This would be a true paradox. One resolution to this paradox is to postulate that only self-consistent histories are allowed. With this postulate, the rules of the game are turned around. We can ask whether a particular physical theory allows self-consistent evolution that is also consistent with its equation of motion. We should also be aware that many physical theories with different equivalent formulations can give different results in the presence of closed time-like curve. Therefore, when determining the effect of closed time-like curves on a particular theory, we have to define the theory very carefully. If you like this video, do subscribe.